Now that we've discussed the motivation for and the structure and functionality of the interpreter pattern, let's go ahead and take a look at its implementation in C++. We'll start by taking a look at the expr hierarchy, which is an inherited set of classes that define the terminal and non-terminal expressions used to create a parse tree from the input provided by the user. We'll begin with the expr abstract base class, which is inherited by the other classes we'll look at in just a moment. This class defines a couple of methods that will figure prominently in both the interpreter pattern and also in the builder pattern. And those methods, not surprisingly, are interpret and build. Let's now take a look at the number expr, which inherits from expr. And this is used to define the number terminal expression and be able to implement it properly in the context of the interpreter pattern and builder pattern. The way this works under the hood is it has a single data member called number, which is set by the constructor. And when we interpret a number expr, it simply goes ahead and returns the number as the result of the interpret method. So that one, of course, is very, very simple. Let's now go take a look at something a little bit more complicated, which is negate expr. Negate expr also inherits from the expr abstract base class, but it defines a data member called write expr, which is its child. And the child is set by the constructor. And when you interpret a negate expr, which is used to represent unary minus, it goes ahead and calls interpret on the right child to get its value, and then it simply negates the result using the unary minus operation. So that's what it means to interpret a negate expr. We'll now take a look at yet another abstract base class. This one's called binary expr, and it's used as the root of a sub-hierarchy for dealing with binary operations like subtraction, addition, multiplication, and so on. And as you can see here, it defines two data members, left expr and right expr, and those are set by its constructor. If we take a look at multiply expr, that's actually a derived class that inherits from binary expr, and it handles the multiply operation non-terminal expression. So as you can see here, the constructor for this multiply expr class goes ahead and takes its two parameters and passes it up to the superclass, to the abstract base class, which is binary expr. And its interpret method is quite interesting. What it does is it first interprets the left-hand expression, it then interprets the right-hand expression, and then it multiplies the results of those two interpretations together to form the final result for interpreting a multiply expr. So now that we've looked at the expr hierarchy, and of course there's other classes too, like divide expr and subtract expr, that basically mimic what multiply expr does with the appropriate substitution of the correct operation. Let's go ahead and take a look at post-order interpreter. So post-order interpreter inherits from interpreter impl, which we'll look at more in just a minute, and that defines an interpret method. And here's what the interpret method does. The interpret method has three steps. It first takes the input that's provided by the user and builds a parse tree corresponding to that input, and it stores it in a unique pointer, as you can see here, so that memory management is handled automatically. Then, assuming that there is, in fact, a parse tree, it's not empty, then there are two other hook methods that get called. One is called optimize parse tree, and this is an optional method that can be overridden by a subclass of post-order interpreter if it wants to do additional things with respect to optimization. We're not going to talk much about that here, but it's a feature that could be used if you needed to optimize the parse tree in some way. And then the final method is build expression tree, and that takes the optionally optimized parse tree and then goes ahead and builds an expression tree from that parse tree. And we'll talk more about how that process works when we discuss the builder pattern here in the next lesson. You'll note that there's actually another Gang of Four pattern showcased here in the implementation of interpret. Interpret is a template method from the template method pattern, which means it defines a fixed set of steps, which are then implemented by the hook methods, or so-called primitive operations. In this case, interpret is the template method, so it defines the steps. And then the steps are build parse tree, optimize parse tree, and build expression tree. And those steps could be changed by further inheriting from post-order interpreter and overriding them to do other things. So this is a good example of yet more high pattern density that we've come to know and love in the expression tree processing app case study. Now let's go ahead and take a look at build parse tree. So this is going to take the input from the user, such as 5 minus 3, 4 plus times, and it's going to go ahead and build the corresponding parse tree that relates to that input string. In order to do this, it's going to use C++ STL stack. It'll be a stack of expr pointers, and this stack will keep track of the intermediate and final expressions that we're building. And I'll first kind of walk through it from a code point of view, and then I'll kind of walk through it from a visualization point of view, so you really get a good feeling of what's going on under the hood. The way this works is we have a little iterator that is going to take the input string and the stack, and then it's going to iterate through all the elements in the string, and it's going to go ahead and push and pop expressions, or maybe a better word is sub-expressions, on and off the stack. And we'll take a closer look to see how that behaves in just a second. When it's all done, it will have one item on the top of the stack, which will correspond to the parse tree. And so we then take the top item off the top of the stack, which will contain the complete parse tree. It doesn't actually pop the item off the stack. It just gets a pointer to the top item on top of the stack. So that's the root of the parse tree. Now let's take a little visualization tour through what's happening under the hood. I think this will help make it a little bit more clear what's going on. So assuming for sake of argument, we have 5 minus 3, 4 plus times as our user input expression. Here's how the post order interpreter is going to behave with respect to the code snippet we just walked through. The first thing it's going to do is it's going to go ahead and create a number node or a number expr with the value 5, and it'll go ahead and push that onto the top of the stack. It will then go ahead and see the negate symbol, which, as you may recall, is the little squiggle, and it'll pop the number expr off the top of the stack and then push the negated expr on top of the stack. So now we have negate expr, which is going to reference number expr for the value 5. The next value we'll see will be another number, so we'll end up creating a number expr that corresponds to the value 3, and that gets pushed onto the top of the stack. So you can now see the stack has 2 elements on it. Then we see the number 4. We make yet another number expr and push that on top of the stack. So now we have 3 elements in the stack. The next symbol we're going to see in our input will be a plus symbol, and that will cause the top 2 items to be popped off the stack, an add expr to be created, and then the add expr is connected to the number expr for 3 and the number expr for 4 and push back on the stack. And then finally, we go ahead and see the multiplication symbol. That will pop the top 2 items off the stack, which of course will be the add expr subtree and the negate expr subtree. We'll make a new multiply expr object and then connect negate expr and add expr to it as its left and right children, respectively. And that will end up with what we see here in this diagram, the final parse tree, and the root of the parse tree will be the top item in the stack. At this point, you could go ahead and call the interpret method on the root of the tree, and it would go ahead and compute the yield of the tree, which of course in this case would be the value minus 35. And it's all very clever and cool how it works by using the interpreter pattern to basically create that parse tree, and then we can interpret its value. So now let's go ahead and take a look at a piece of the code that actually builds the parse tree in C++. And this code is what we saw back over here used along with this loop. So this loop is actually going to go ahead and use the iterator we're about to look at in order to carry out this interpretation process. So we define something called a post order iterator, which is just a nested class inside of post order interpreter, and it implements or inherits from the iterator class that's defined in STL. We're defining a forward iterator that's going to be dealing with expr pointers. The constructor, as you can see, goes ahead and squirrels away the input string and the stack in local data members that are fields in the class, and it also sets the index data member to 0. So we're going to start looking at the beginning of the input string. And you can see down here we've got index, which is the place in the string that we're looking at, the string pointer, which is keeping track of the string itself, and then we have a pointer to the stack. So here's the not equal operation. This is the inequality operator that's used to tell when we're at the end of our iteration. And we're at the end of the iteration when the index that we're using as this little counter is going to be equal to or greater than the input length. So as long as the index is less than the input length, we're not done. So it's not equal yet. And all operator plus plus does, this is of course the pre-increment operator plus plus, it simply goes ahead and advances the iterator by incrementing index by 1. Now let's go ahead and take a look at the dereference operator. This is the one that does all the heavy lifting here. You can see it's going to return an expr pointer. So what it does is it goes ahead and takes a look at the character, that's the next character in the input, starting, of course, at the 0th character, which is the first character in a C++ string. We're then going to go ahead and skip over any leading white space. And when we're done, we take a look and see, what have we got? Have we got ourselves a number? Have we got ourselves a variable? Have we got ourselves an operator like plus or minus? If we have a number, then we're going to go ahead and call a factory method called makeNumber. And we'll look at what makeNumber does in a second. What you can imagine it's going to do is it's going to look through the rest of the input string to find the number, peel that off from the input string, and then update the index accordingly so it'll continue parsing at the right place after we create the number. We now go ahead and take a look at what happens when we get something, say, like a plus or a minus or divides or a times symbol. So in that particular case, we go ahead and take a look at the top item on the stack, which will be the right expr, and then we pop the stack so that we're going to ignore that. And then we switch on the character that we're looking at. If we have a plus character, that means we're doing the plus operation. So what we do in that particular case is we call a helper method called makeExpr, which we're going to look at in a second. And this is actually a template method, and it's very cool. And it's going to go ahead and process the particular expression, which in this case will be an add expression. If we get the minus sign, we'll do the same thing, except we'll call makeExpr, except this time for subtractExpr, and so on and so forth. Same thing applies for the negateExpr as well, and the divideExpr, and the multiplicationExpr, which I'm skipping here for purposes of simplicity. You'll notice that the negateExpr only has a right child, so it doesn't need to pop anything else off the stack. So speaking of popping things off the stack, here's the makeExpr member template function, and you can see what it does is it takes the stack, and it also is going to take the right expr, and it's going to go ahead and read the current item off the top of the stack and store it in this local variable, which is an auto, of course, but it's an expr star under the hood. It will then pop the item off the stack, and then it'll go ahead and make ourselves a new object of type T. And if you look back over here, you can see we cleverly use this member template function in order to parameterize the type of object we wanted to create, an add expr, a subtract expr, and so on. So that'll go ahead and make us the appropriate type of expr, concrete expr we need, passing in top and passing in right expr. And that'll be returned as the result from makeExpr. What we're going to do now is take a look at the actual source code. This is in the interpreters folder inside the expression tree project. And the interpreter is playing the role of the abstraction class in the bridge pattern. You can see it just has a single method called interpret, and it has a ref counter to the interpreter impl. So let's go ahead and take a look at the implementation of an interpret. It's pretty obvious what it does. It just forwards to the implementation class using the good old bridge pattern as our guide. If we go take a look at interpreter impl, it's got an interpreter context, which is used for various things like keeping track of named variables and so on. And then it's got the interpreter impl. And this plays the role of the implementer base class in the bridge pattern. So this is where all the different kinds of concrete interpreters will derive from. So post-order interpreter, in-order interpreter, and so on. And as you can see, it's got these virtual methods, build parse tree, optimize parse tree, and build expression tree. And it also keeps track of the interpreter context that's associated with what it's doing. Here are the different interpreter implementations, at least the definitions of the classes. We have in-order interpreter that knows how to process an input string that is comprised of in-order or infix expression, characters typed in by the user. And you can see it's got a whole bunch of stuff in there. And then down here, we have the post-order interpreter. And that's the one we're going to focus on because that's the one that's most obviously related to the Gang of Four interpreter pattern. You can see here it also has build parse tree and build expression tree. We don't implement optimize parse tree. We don't need to do that. And then nestled inside of post-order interpreter is the post-order iterator, which we looked at before. And that's what actually walks through the input string from the user and then creates the corresponding parse tree from the characters the user has provided. And we kind of looked at that just a second ago. Okay, let's go ahead and take a look at the key parts of the interpreter impl. So here's build parse tree. You can see it basically does what I showed you before. We go ahead and make an iterator to the beginning of the input. And if you look down here or look up here, you can see that here's the factory method that makes us a little post-order iterator based on an input string and the stack. And end just is kind of a no-op just to hold everything together with good old STL syntax. And then we just walk through as we looked at when we did the code walkthrough earlier in this part of the lesson. And it basically takes each character, looks at what it is, and then it performs the operation to pop things off the stack and make the appropriate type of expr concrete node and then push it back on the stack. And when we're all done, assuming we actually got something that was non-null, we return the top of the stack. Here's build expression tree. Build expression tree was, as we are going to see when we talk about the builder pattern, is going to take the parse tree that's created by build parse tree here, and then it's going to simply tell it to build the corresponding expression tree. But that will get us too far ahead of ourselves because that's going to be covered next when we go and talk about the builder pattern.